Welcome to section 3.6, linear inequalities in two variables now, and systems of linear inequalities. So linear inequalities in two variables, we know what an equation looks like with an equal sign. So for instance, something like that, that's a linear equation in two variables, but now we have an inequality. So we're just going to replace that equal sign with a less than, a greater than, less than or equal to, greater than or equal to, something like that. And then we have our linear inequalities. So we know that if we were looking at all solutions to something like this, 2x plus 3y equals 6, well, there's infinitely many, right? Because we have all these ordered pair solutions, and we can look at the graph to see all the solutions. Likewise, over here, now that's an inequality, we're going to rely on the graph to show all the solutions. So we graph the solution set of linear inequalities in two variables. So let's look at this first example, y less than x minus 4. Our first step is to graph the corresponding equation. So our first step would be to graph y equals x minus 4. I'm going to use slope-intercept. So our intercept is -4. And then our slope is 1. So we go up 1 and over 1. Up 1 over 1. Okay? Just like that. The other thing, before we connect our dots, and this is like a rule for all of them, if we have strictly less than or strictly greater than, y equals x minus 4, notice this is equal to. So a line won't be included in our solution set to the inequality. So if that's the case, then when we draw our line, we're going to draw a dotted line. If our line is included, y is less than or equal to, or y is greater than or equal to, that's when you draw the solid line. So then something like this. All right, so in our example, we have a strictly less than. So when we draw this line, we're going to draw a dotted line. And then that's going to tell us this line isn't actually part of our solution set. Y is strictly less than. Okay, so now we have two regions on our graph. A line across an xy plane breaks it up into two regions. We have the region on top of the line and the region down below. And now all the points above the line or all the points below the line will work. It's all or nothing, right? So either everything up here works or everything down here works. All ordered pairs down here work. So how we determine what region we're going to be considering for our solution set is we use a test point. All right, so again, this is an all or nothing situation. And a great test point to use, first of all, it has to be off the line, and 0, 0 is off the line. So let's use that one. So a test point is literally a point, an xy point on our graph, and the best point, the easiest point to choose is 0, 0, as long as it's not on the line. All right, so let's see how this works. We have y less than x minus 4. We're going to see if the point 0, 0 satisfies this line. So when y is 0 and x is 0, does that ordered pair satisfy the inequality? All right, so is 0 less than -4? No, it's not less than -4. So it's false. So let's go back up to our graph. So that means 0, 0 isn't part of the solution. It doesn't work. So that means that this half that point 0, 0 is in, none of these points are going to work for our inequality y is less than x minus 4. And that actually means everything on the other side of the line will work. For instance, let's choose a point. Any point, we can just do maybe 3, negative 2. 3, negative 2 is going to satisfy that inequality. So let's just kind of check that out. So 3, negative 2 is in the other region. So y equals negative 2, x equals 3. Is negative 2 less than negative 1? Yes. It satisfies that inequality. Okay? So again, this means all or nothing. So if that one point works, it means everything is going to work in this region below the line. So we're going to highlight everything to let the reader know that this is our solution set. Okay? And then we're done. Okay, so if we want to write ourselves a note, just say what we did here when we said no, it was false, then it's time to shade the other region. If it's true, like over here, shade that half or that region. All right. So again, 0, 0 was in the half that didn't work. 3, negative 2 is on the other side of the line. Let's look at this example. We have 3x minus 2y is now greater than or equal to 8. And we are going to graph our solution. So first, let's start off by graphing this line. Normally when it's in this ax plus by equals c form, we can look at the y-intercepts. All right, there's the corresponding line. But I know we're going to get a yucky x-intercept, right? Because 3 doesn't divide into 8. So because I'm predicting that, I'm going to solve for y. All right, so again, I'm going to solve for y. I'm not going to graph this using the x and y intercepts because we would get 8/3 for an x-intercept. If you don't believe me, try that out really quick. Plug in it, y equals 0. So because x and y intercepts don't work, let's put it in y equals mx plus b, solve for y. Subtract that 3x from both sides and divide by 2. Oops, not just any 2, negative 2. So negative 3 divided by negative 2, the negatives cancel, and 8 divided by negative 2 is negative 4. All right, so now we're ready to graph our line. I'll graph it in green. So our y-intercept is negative 4, so we'll start there. And rise over run, we're going to go up 3 and over 2. Up 3 and over 2. Okay, so what kind of line are we going to draw? A dotted line or a solid line? This time it's going to be solid because it's greater than or equal to. So this time our line is included in our solution set. So we're going to do a solid line. And now it's either going to be the region on top or the region down below. And how we determine this, it's all or nothing. So we can take any point in any of the regions and determine which region to shade. Let's try our favorite point, 0, 0, since it's not on the line. So let's use test point 0, 0. And we would want to know, is 0 minus 0 greater than or equal to 8? So is 0 greater than or equal to 8? No. Okay, so 0, 0 did not work. And again, it's all or nothing. So it means if we try out any point in this region above the line, it will not satisfy this inequality. It also means the other region has to work. So the other side is our solution. And so we indicate that by highlighting that region. All right, so you can write yourself a note because we said no, highlight other region, or the other side, other half, all synonymous. Okie dokie, let's look at another example. Here we have y less than 4. And I've noticed we don't have an x-coordinate, it's just y less than 4. So that means it's either a horizontal or a vertical line. And if we have a constant y value, y equals 4 is right here. All right, so this is going to be a constant y equals 4, so we're looking at a horizontal line. And why am I drawing dots? Yes, because it's strictly less than. So this is telling us our solution set does not include the line. Okay, so intuitively, all y values less than 4, well, that's going down. So we can actually just highlight the region just based kind of like on an intuitive understanding of y less than 4. If for some reason we didn't see that, again, we can always choose a test point 0, 0. And when we plug in y equals 0, we get a true statement. So that means all ordered pairs in this side are going to be part of our solution set. So we're going to highlight the region below y. Okay, so that's a single inequality. We're going to be looking at a system of linear inequalities now in 2 variables. And again, we're going to be graphing our solution, and the solution to the system is going to be the intersection of the graphs of all the inequalities. So let's look at this example. We kind of have to do twice as much work now. We're going to solve this system of linear inequalities, and we have to graph twice. So I'm going to graph 3x minus 2y first, and I'll use green. So we'll do the corresponding equation. And then I see that 3 and 2 both divide evenly into 6, so I'm actually going to use the x and y intercepts this time. I think that's going to be a quick strategy. So our y-intercept when x is 0 is going to be negative 3. And when y is 0, our x-intercept is 2. All right, and we're strictly less than, so we're going to do a dotted line. And then let's do a quick test point as well. We can test 0, 0 since it's off the line. If it happened to be on the line, we would just have to choose a different point. All right, and when we plug in 0, 0, is 0 less than 6? Yes. So we're going to shade the region that contains 0, 0, because 0, 0 is true. That means all of the ordered pairs in that region will be true. Okay, so let's see what's next. Now we have to graph the other one. 4x plus 3y equals negative 12. And again, 4 and 3 go evenly into negative 12. So I can do my x and y intercepts this time. When x equals 0, y will be negative 4. And when y is 0, x will be negative 3. And again, we're strictly greater than, so let's do a dotted line. And we'll try out the ordered pair. Again, 0, 0 is not on that line, so we'll plug in the ordered pair 0, 0. And we get 0 greater than negative 12. Is that true? Yes. So that means 0, 0 satisfies that inequality, so that means all ordered pairs in that region will satisfy the inequality. So we're going to highlight everything. All right, so we know that solutions to systems, the ordered pairs have to satisfy both. So we're going to be looking at the overlap. Anything that we colored both blue and green are going to be our solution. Okay, and make sure when you do this on your exam, you're really clear about what your solution set is. If you just start coloring everything with a gray pencil, I'm not going to know where to look. So either you guys bring some colorful highlighters so you can point to the region or something like this. But we're looking at this yellow region we just highlighted. All right, and that's how we solve a system of inequalities. Let's look at this next example. And this is our final example. And notice we can do this for 3 inequalities. All right? And it's the same thing. So let's see how we're going to do this. Let's graph x greater than or equal -2. That's going to be a solid line at x equals -2. That's our vertical line. All right, and if x is greater than, all x values greater than, that means we're going to the right. So you can do a test point, or you can just intuitively think about it. All right, and rather than highlighting, I'm just going to do arrows for right now, or else we're going to have a lot of highlighting. All right, y less than 3, it's going to be a vertical or a horizontal line, and it's going to be dotted. And again, y is less than 3, so all y values less than 3, we're going to be going down. So far it looks like it's just this little region right here. This is where our common overlap is right now. But we have one more line. We have y greater than or equal to a third x minus 2. We'll do that in green. And we'll do y-intercept -2 and a slope of 1 over 3. Slope of 1 over 3. All right, and we're doing a solid line because it's greater than or equal to. Okay, and then let's use a test point. We can use the point 0, 0 for that last one. So is 0 greater than or equal to -2? And it is. So that means this 0, 0 works, so it means all points above the line will work. So again, you can do something like this, just arrows, so we don't have a bunch of crazy highlighting. Okay, so this is telling us, look where all the arrows are pointing. The only region that's going to have red, blue, and green is this region right in here, this little triangle. So we kind of have a bounded region this time. This one would be an example of a bounded region. It's just this triangle. It doesn't go off forever and ever. And notice our examples up here. For instance, this yellow one, this one went on forever. This one was unbounded. It was going to go off to infinity. All right, so when we have 3 equations, 3 or more equations, sometimes we can have bounded solution sets.